Now we're going to start looking at superposition, and then we'll look at lots of things to do with superposition. If you're going to observe superposition, which is the adding together of waves, then you need waves of the same type. So two waves on a string, they can superpose, they can add together. Sound waves, they can superpose, if you have two sound waves. And two microwaves, they can superpose, and so on. You can't superpose sound with waves on a string. And you can't superpose sound with microwaves, and so on. So you need waves of the same type. Now whenever superposition occurs, the waves add together and you get a resultant wave formed, which has the sum of the displacements at each point. So remember that wave displacement can be positive, it can also be negative. So that means that if we're adding up two positive displacements, they would be a positive resultant, but you can have so the total size of the displacement gets larger. But if you have a positive and a negative, then the sum will cause you to take them away, and so you can get a smaller resultant displacement. Here are two waves. I have a green wave and a red wave, and I'm going to graphically work out the resultant of that superposition. What I'll do is work out the resultant displacement at several points along the wave, and then I'll join those dots with a nice smooth continuous wave to get my resultant. In this example, I'm going to show the process of doing it for 2 points, and then I'll just plot some other points. So here's, at this point, the resultant displacement. Now, the green wave has a displacement of up to here, and the red wave has a displacement up to here. They're both positive, so they're going to add up to give me a resultant positive displacement. So what we're going to do is we're going to move this red line here up so it's in line with the green one, and plot that as a point. Okay, so the resultant displacement is here because it's that plus that. Okay, now let's do this point, and I have a positive displacement and a negative displacement. So here I've got to do that take away that, or that take away that. But I can see that this displacement, this negative displacement, is larger than this one, so I know it'll be a resultant negative. So let's move that up so the top's aligned, and so I'm taking that green one away from the red one. It gives me a point there. So I've plotted 2 points, the resultant displacements are a couple of points. Now I'm going to do some more along here. So plotting these points along here. Okay, so I'm getting a very interesting resultant wave. Now all that remains to be done is to connect all of those points. So let's do that. And this thick grey line here, that's my resultant wave. So when I have my green wave and my red wave here superposing, at the instant they're in these positions, I would not see either the green wave or the red wave. I would just see this black one here, or the grey one here. I wouldn't see the waves that formed it, I'd just see the resultant. So you need to appreciate that fact. Okay. Now let's see what happens, what you can ascertain if you're looking down on top of the wave. So we're using wavefronts here. Let's take a top-down view. Remember that 2 wavefronts, that means you've got 2 peaks. So where my wavefronts are crossing, I have 2 peaks at the same point. And where halfway between the wavefronts are troughs. So at this point here, I have 2 troughs meeting at the same point. So that'd be like, where the 2 peaks are, I've got a peak plus a peak, so I'll get a double peak. And where I have 2 troughs, I get a trough plus a trough, give me a double trough. And then at these points here, this is a peak plus a trough. So peak plus a trough gives me 0. And then peak plus trough, peak plus trough. So you can work out by looking at each of those points whether you have 2 peaks, or a peak and a trough, or 2 troughs. Okay, so different types of superposition. Now let's look at phase difference. Phase phi is a fraction of a cycle, wave cycle, that has been completed. Now, that means that one full cycle, and we measure this in degrees and or radians, so one full cycle is 360 degrees or 2 pi radians. So if only half a cycle has been completed, then the cycle would be, or the amount of cycle that can be would be 180 degrees or pi radians. The phase difference is the difference between the cycle completion of 2 oscillations or 2 waves. Okay, so here we look at phase difference is taking 2 waves, and if at this point one wave has completed one full oscillation, the other one has completed only half, then there's a 180 degree phase difference between the two of them. The two extremes of the phase difference are your 2 waves could be in phase or they could be in anti-phase. And we normally consider, or we consider in phase and anti-phase situations a lot in waves, so those are the key ones. Okay, let's take 2 waves here which are going to be in phase. So I have my green wave here, and then I'm going to take an identical wave which has the same amplitude and the same frequency. And these 2 waves, they are in phase. So the delta phi, the phase difference, is 0 degrees. They're doing exactly the same thing at the same time. One is not ahead or behind the other. They're completely overlapping. Okay? Now when that happens, when your waves are in phase, you get constructive interference take place. Because if you add up all of the displacements, just as we were doing for superposition, there you see we've got 0 here, we've got 2 peaks, so we get a double peak wave, double trough, double peak, double trough. So our wave amplitude is twice as large as it was before. So these 2 waves, they're reinforcing each other, they're working together. So this is constructive interference. Okay, now let's consider another situation where our waves are no longer in phase, but this time they're in anti-phase. So delta phi here is 180 degrees. The green wave is going straight into a peak, whereas the red wave is going straight into a trough. So where a peak occurs here, a trough occurs there. And then where a peak in the red wave occurs, a trough in the green wave occurs. So they're doing the opposite thing at the same time. They are working against each other, they're cancelling each other out. So here, delta phi is 180 degrees, and we call this type of interference destructive interference. So we have constructive and then destructive interference. Okay, and then you can also have something in between that. These waves are out of phase, they're not in anti-phase, but they're just out of phase, and delta phi is 45 degrees here. So the red one is lagging behind the green wave by an eighth of a cycle, so it's 45 degrees behind. Okay, that's what phase and phase difference is. This one would give you not a complete reinforcement of each other, it wouldn't give you a complete cancelling out of each other, it's somewhere in between. There's places of reinforcement and some places where they're working against each other and taking away. Okay? So you would use this to work out how your waves are matching up at a point, and then work out what the superposed wave would look like at that point. Okay, so now that's phase and phase difference. Let's look at how path difference affects how much the wave cycle has been completed at various points when you have multiple sources of waves, and then so you can see what the phase difference is and then what the type of interference is. If you have 2 sources of the same type of wave, note I'm talking about the same type of wave because we want them to interfere, we want them to superpose. The path difference affects the phase difference. Okay, so the path is the path taken by the wave from its source to the point where you're observing. I'm going to call this source S1 and this is S2. And the path from S1 to the observer is there, and the path from S2 to the observer is there. If you have zero path difference, i.e. both paths are exactly the same, like in that situation there, then there is no phase difference. So the phase difference is 0, and they are arriving in phase. They're doing exactly the same thing at the same time. There's been exactly the same number of peaks of troughs along this route and this route. So by the time the waves arrive there, they're doing exactly the same thing at the same time. Now that is assuming that these two sources are also in phase. Okay, so I'm assuming that my waves are that, and that's usually what happens. And we'll talk about coherency when we look at two-source interference. So yeah, these are in phase here. That means they'll be in phase here, or wherever the path difference is 0, and that would be anywhere along this midpoint between the two sources. So you get constructive interference because they're in phase. Now if you find other points where the path difference is equal to some integer multiplied by the wavelength, then they'll also be in phase at those points as well. So if one wave has had to travel an extra wavelength's worth of distance than the other wave, then it's still restarting its cycle, as it were, so they're both then doing exactly the same thing at the same time. So wherever you have the path difference equal to what the whole number of wavelengths further than the other, then you get the waves in phase and constructive interference. And if the path difference is such that one wave has had to travel a whole number of wavelengths plus a half wavelength, then they'll be in antiphase and you get destructive interference. So here, if the path difference is n lambda or 0 lambda, which accounts for both of those, then you get constructive interference. And at any points where it's n plus a half times lambda, then the waves are in antiphase and you get destructive interference. And if you look at various points around, then you will see that you get some places where you get constructive interference, some places where you get destructive interference, and you can get some interesting patterns forming. Okay? So if I move my position there, so let's take an example here. I move my position, the two sources producing waves of wavelength ½ meter. Now if S1 to the observer, that distance there, is 12.0 meters, and S2 to the observer, that is 9.75 meters, then the path difference is 12 minus 9.75, which equals 2.25. And that is 2.25 meters, is 4.5 times my wavelength. So that tells me that this is where this final situation here, n plus a half lambda, so that n was 4 plus the half wavelength. That tells me that the waves at that point, they're arriving in antiphase and they're producing destructive interference. Okay, so that's an example using a wavelength and path differences. Alright, so let's look at a very important case of this path difference and phase difference, which is Young's double slit experiment. And this experiment is important because it's a classic proof that light is a wave and not a particle. But Newton thought that light was a particle, and you can see towards Young, the experiment was named after Young. He came after Newton, and Newton thought that light was a particle, and Newton, he's a legend in physics, so you don't easily disagree with Newton. But this experiment was proof and was eventually accepted that light was indeed a wave. So for this experiment, you need coherent sources of light, If you have coherent sources of light, it means that they have a constant phase relationship. So go back to that situation where I had S1 and S2, that would mean they're either always in phase or always in antiphase. The phase relationship is constant. Okay? For this particular experiment, we need coherent light sources, but we also need them to be in phase to produce the exact pattern that we want. Anyway, so we need coherent light sources, but the trouble with white light is that the light is produced randomly, and so that is not coherent. You can't have two bulbs, for example, giving you coherent light. That's not possible. The light is produced randomly. So the experiment has a single slit, and the purpose of the single slit is it gives you a single source of light which is coherent, because the slit is so narrow you've confined the light down to a single source, and that gives you a coherent source of light. So the light will come out the single slit and it will go into the double slits, so you then have two sources of coherent sources of light. So two coherent sources of light. There's my source of white light, there's my single slit, and my double slit, and then I have the light from the double slit is going to shine onto this screen and produce a pattern. Okay, and you get an interference pattern occurring on the screen. Now we said when we were looking at superposition in general terms, if you have two waves of the same type, then they can interfere. Light is a wave, so it can interfere. So it may be surprising to you that light can cancel out and give you dark regions, but indeed it can. This experiment shows. So there's the light coming out of my single slit. By the way, this is not to scale. So there's my light coming out of the single slit with wavefronts there representing that. The light then enters into the double slit, so I now have two sources of coherent white light, and those wavefronts from each source are indicating, we can use those to indicate, find out where the light it produces constructive interference and destructive interference, and then we get regions projected onto the screen where we get maximum signals and minimum signals. So these are the maximums where my two wavefronts are crossing, two troughs, two peaks, two troughs, and so on. So we get this whole line of constructive interference. We get another whole line of constructive interference there, and another whole line of constructive interference there. So what we're going to get here are bright spots on the screen. And then we have, halfway between as well, you would also have minima here. So we've got a wavefront plus the midpoint of the wavefront, so that's a peak plus a trough, and you get a whole line of peaks and troughs combining there to give you regions where the waves cancel out. So you do indeed get bright spots and dark regions in between them. And that's what interference pattern is. This is a photograph of the experiment done with red laser light. So you can see these bright regions, and then in between you've got these dark regions. So the light is giving you constructive interference, these nice bright regions here, and then in between those there are these dark regions where the light is cancelling out to give you darkness. So light can interfere, and it's this conclusion, this observation of light interfering, the fact that it can interfere, that means light must be a wave. Particles of the same type don't normally interfere to reinforce or to cancel each other out. So you don't have two electrons, and they don't constructively interfere and destructively interfere. So we don't normally observe that. So that's not how particles are supposed to behave. So it seems that light is a wave. And that's why it's a classic proof of light behaving like a wave. Okay. Now let's look at let's look at the layout and how the equation relates to the layout. So we have our screen, we have a double slit there, and this is the fringe pattern observed here with the bright regions and the dark regions in between. This dotted line just marking out the central point there, the centre of the double slit and the central bright spot that we observe. This distance here between the two slits is called A. The distance between the slit and the screen is D. And then the distance between two neighbouring bright regions is X, or it could be two dark regions as well. You can take that measurement instead. And that's X. And the equation is the wavelength of the light is equal to AX over D. So if you're working with the red laser light, such as the one I showed you, then you could work out the wavelength of the light from this experiment if you know how far apart your slits are, and measure this X and you know how far D is. So you can use that to work out the wavelength of light. And these slits, they need to be very narrow, as close to the wavelength that you'll be using as possible to give you lots of diffraction, because you want your light to spread out from each source so that they cross over each other and you get the superposition occurring to give you that interference pattern. So narrow slits maximise the diffraction to get a nice big region of interference. Okay, let's look at some other cases of two-source interference. There are some experiments that you need to know about, so let's look at 4 of them. Firstly, we've got a variant of Young's double slit experiment. Young was using white light, but we often use laser light. So you could use red laser, you could use green laser, you can use various colours of laser light. And laser light is coherent, so you don't need the single slit, so it's a bit easier to work with. You don't need the single slit, just pass your laser light through the double slit, and that'll give you your interference pattern. Monochromatic means single colour, so it gives you a single wavelength of light. So you might be in the red region, so 600 nanometers, for example. Sound. And here you have 2 speakers connected to a signal generator, giving you a single frequency of sound in each loudspeaker. Again, they need to be coherent. And here, what you would do to observe the interference pattern is walk parallel to those 2 speakers, and you could hear regions where it's loud, regions where it's quiet. Then we have microwave two-source interference. Here you have a microwave transmitter, and you have some aluminium plates. Aluminium will cause microwaves to be reflected. They can't pass through the aluminium plates. And if you put a couple of gaps in there, then that gives you your 2 sources of microwaves. Then with a probe, you can move it parallel to those slits, and if the probe is connected to some kind of meter, or you can have it connected to a speaker as well, then as you're moving the probe parallel to those slits, you will observe regions of maximum signal and regions where it's a minimum signal. If it's the meter, then you'll see it in the signal strength. If it's a speaker, then you'll hear regions where the signal is loud and regions where it's quiet. But remember, you cannot sense microwaves. You can't see them, you can't hear them, you can't touch them, you can't smell them, you can't taste them, okay? So you need some way to convert it into something that you can sense. You need a probe connected to the meter so that you can see the needle, the signal strength on a readout, or you need a speaker so that you can hear it, or an oscilloscope. Okay, so you need some way to convert it, and therefore you need to make sure that's clear. You can't hear microwaves. And lastly, a ripple tank. This is a picture of looking down on the ripple tank. Here are 2 sources of water waves, and you can see that interference pattern quite nicely there. You've got these very distinct ripples here going along this central midpoint here, and that's because you've got a double amplitude wave along there, because you've got constructed interference, and then these regions here where there's virtually no displacement, there you've got destructive interference. So water in a ripple tank. And that shows you that top-down view rather nicely, like wavefronts. Okay, diffraction gratings then. Here you have a series, not of just two slits, but many slits which are all parallel to each other. So you could, if you're dealing with light, you could be looking at something like 620 lines per millimetre. Right, if you pass white light through a diffraction grating, then what you would observe on the screen is a central bright spot, which will be white, and then you would get spectra to the side of it. So you get some spectra over there, and then you get the inverse spectra over there. The blue light faces inwards, red light faces outwards. And the reason that you get spectra on the diffraction orders to the side of the central one is because each colour has its own wavelength. And you'll see that the angle that the light is diffracted to is a function of the wavelength. So longer wavelengths have a larger diffraction. So red light with the longest wavelength is diffracted the most, and blue light and violet light with the smallest wavelength is diffracted the least. So they all diffracted a slightly different amount, and that spreads them out. If you use monochromatic light, then you just get a series of single colour spots. So if you pass a green laser through your diffraction grating, you'll get these green spots. So you get a central bright one, and then you get some to the side as well. But they're all green because the green laser light only has green light in it. As I said above, these maxima, they occur at angles which depend on the wavelength. And they also depend on this diffraction order and the distance between the adjacent slits. So this is the equation. D sine theta is equal to n lambda. Okay, and so red light, longest wavelength, gives you a larger sine theta for a given D and n, and that means that theta will be larger. Okay, let's look at the diffraction order n0 is for the central maximum. So if you put n equals 0 there, then you'll get an angle of 0. That's what you see. You get a central white spot if it's white light. So all the wavelengths are not diffracted. So you just got that, all of the wavelengths meeting at that point to give you the central bright spot. Yeah, let's look at the top-down diagram here. There's our source of white light. Here's my multiple slits and the screen. This is the setup you would use to determine the wavelength of light, or you could use to determine the wavelength of light. You would use monochromatic though for this case. So here we've got a much more complicated arrangement of wavefronts, so multiple sources here, and these wavefronts. You then look for where you get wavefront plus wavefront plus wavefront, giving you a maximum, and then where you have a minimum as well. So you get a pattern of maxima and minima. There's your central maximum. Just to the side of that you have your minimum, so it's dark in those regions. And then you have your first order diffraction orders where n equals 1, then more minima, then you have n equals 2 diffraction order, so a couple more maxima. So it's a symmetrical pattern around this central bright spot. So if you know the slit separation, which is D, and you can measure the angle to a maximum at a specific diffraction order, so therefore you also know n. So if you measure this, and from this central line, if you measure this angle here, well, let's just mark up the angles actually. So you've got theta 1 here, is the angle from the maximum, the central maximum, to the first order diffraction order. So you know theta, and this is n equals 1, the first one from the centre. So you know n, you know theta, and you know d, therefore you can work out the wavelength. As I said, with white light, you're going to have all of the colours spread out, so you wouldn't be able to do this experiment with white light. You would need to use single colour like red or blue or green, something like that. And then you can use that to calculate wavelength. Okay, diffraction gratings. Now, they are usually characterised by the number of lines per millimetre. So D, the distance between each slit in millimetres, would be 1 over that, and therefore one thing you need to remember, because D is in millimetres, is to convert that into metres once you've worked that out. And the maximum theoretical diffraction order is at theta equals 90 degrees, because the light isn't going to be diffracted backwards. So at that maximum theoretical diffraction order of 90 at 90 degrees, sine theta is equal to 1. So now your equation becomes n max, the maximum diffraction order, is d divided by lambda, because the sine theta bit has come out as 1. And you use that to work out what the actual highest diffraction order would be. So if you have your D, you have your wavelength that you're working with, work out what n max is. Now, you usually will get some decimal value, like 3.54, ... But the diffraction orders occur at integer values. So if it was 3.54, your actual maximum is at 3. And the diffraction gratings are useful. They're the instrument of choice for separating out colours of light. So if you take light produced by some gas lamp, like a helium lamp, sodium lamp, use a diffraction grating to separate out all of the colours, and then you can actually investigate which colours, which wavelengths are present in the light. So they're very useful, and they can be used in chemistry as well. You can burn elements and see which colours are emitted by the elements. So very useful. Yeah. I'm having to do a second instalment of this video because my camera ran out of storage. So I'm picking up where I left off, and we've just got to standing waves. I'll go through what standing waves are, how they're formed, and then we'll look at some practical applications with strings and pipes. So if we start off then, standing waves are waves that trap energy, and the places where they trap energy we call antinodes, and we'll look at what antinodes are later on. You can say that they're waves that trap energy, or you can say they are waves that have nodes and antinodes. And as I go through how the standing waves are formed, I will be using transverse representations of the wave because they're easy to understand. But that doesn't mean that standing waves can only be formed with transverse waves. They can be formed with longitudinal waves. Okay, what do we need to form our standing waves? We need two progressive waves. They need to be identical as well. They need to have the same frequency, same amplitude, and they need to be moving in opposite directions. Now we need these two waves to meet and superpose. So just with any other case of superposition, we need waves of the same type. So if I'm going to use sound waves, I need to use two sound waves. I need to use two microwaves if I want microwaves to superpose and produce standing waves. So they need to be waves of the same type. And due to the fact that they're moving in opposite directions, that's going to give them a changing phase relationship. So we're going to get a combination of constructive and destructive interference. Now a common misconception, which I'll pick up later, is that the constructive and destructive interference occurs spatially, not temporally. So the wave is going to, we're going to see that when there's constructive interference, it's all the way along the wave. It's not that at some locations there's constructive and some places there's destructive interference. It's all the way along the wave, but then sometime later it'll be destructive all the way along the wave. So hopefully, as I go through it, that will make sense. The other thing here is that because they're moving in opposite directions, the change in phase relationship happens twice as fast than if, like, theoretically you had one wave that was stationary and the other wave was moving past it. Not that you could have that, because obviously we need two progressive waves to form the sunny wave, but the change in phase relationship will happen twice as fast, and that's because their relative speed is doubled. So if the progressive waves had a speed of 300 meters per second, then the relative speed between them is actually 600 meters per second. And the outcome, or the point of that, is to say that the waves will go from being in phase to being in anti-phase twice as fast. Okay, let's take our two progressive waves. I have a red wave and a green wave. They're identical, same frequency and amplitude, moving in opposite directions. And you can see as they were moving past each other, they were going from being in phase to in anti-phase, back to being in phase again. So let's take this situation here, this snapshot, as our T0. So at T0, our waves are meeting in anti-phase. The red wave's at a peak here, and this one's at a trough. The peak, trough for the green wave, and then the red wave. So all the way along, they're in anti-phase. Now let's see what happens a quarter of a cycle later. Oh, sorry, no. And so if we took a snapshot of our wave at this instant, we would see this zero displacement all the way along. Okay? Yeah, now let's see what happens a quarter of a cycle later. They're going to arrive in phase, so the waves keep moving. It's quarter of a cycle later, not the half that we might have thought to go from being in antiphase to phase, but it's actually quarter of a cycle later. And the peaks are lining up, the troughs are lining up, and that's going to give us a double amplitude wave. So if we could see the wave at that instant in time, we'd see this double amplitude wave. Peaks twice as high, troughs twice as low. So it's in phase, and we get this constructive interference. And the constructive interference is all the way along the wave. And you'll see that these points of zero displacement, they're important for later on. We'll see that these are called nodes, but it's still constructive interference. It's a 0 plus a 0. Another quarter of a cycle later then, they will arrive back in antiphase. However, the difference here is, so although we get zero displacement all the way along, the red wave is at a peak here, but back here, which is half a cycle later, when they were in antiphase originally, the red wave was at a trough, and the green wave was at a peak there. So these waves have actually flipped, but it's still antiphase. And then if we continue for another quarter of a cycle, they'll be back in phase, and we get our double amplitude wave. However, there's a double peak here, but it was a double trough. And there's a double trough here, but it was a double peak. So what's actually happening at this location here, where we're getting these double peaks and double troughs happening, is it's going from a double trough up to zero, up to a peak, back to zero, down to a trough again. So we get this oscillation, this very big oscillation happening when we get our standing wave formed. And as I said before, these zero displacements here, when we've got this constructive interference all the way along, but these positions of zero, they're always zero. There was zero here when we're back in constructive interference here, and there was obviously zero when we had the destructive interference because the waves were cancelling out. And those positions are called nodes, where we have zero all the time. So let's look at a diagram of the wave at various times. This solid line here is the wave at a certain time, and then another time later it will be along these dotted lines. Again, a continuation of peaks and troughs, and then it will go to zero, and then it will start forming, instead of a trough here, it will start forming the peak here. Okay? And you can see the nodes very clearly here. We can mark out the nodes. They're always zero. Whatever time you look at the wave, it's always zero there. Midway between those successive nodes, you have antinodes. Now, when you have standing waveforms, you never have two antinodes next to each other without a node in the middle. So you always have antinode, node, antinode, node. It's impossible to have a standing wave with antinodes next to each other or nodes next to each other. So those positions, we have maximum amplitude at those positions. And then you can use the antinodes and nodes to measure out the wavelength. If you go from one node to the next, that's half a wavelength, and if you go from one antinode to the next antinode, then that's half a wavelength. Okay, so we go from a peak to a trough, so we know that's half a wavelength, and you can see that this is as well, because these are sloping down here and sloping up, so they're halfway along. And obviously, if you went from one node to the next and then the one beyond that, that's a full wavelength. Likewise here, going from one antinode, not to the next one, but to the one after that, that's going peak to peak, so that's a full wavelength as well. Also, if you go from an antinode to a node, that's a quarter of the wavelength. Don't make this mistake, as I've kind of hinted at before, nodes are not positions of destructive interference, because when you have destructive interference, it occurs all the way along the wave, and when you have constructive interference, it occurs all the way along the wave. So when we have constructive interference, like when we're at this solid line here, there's still a node there. So there is constructive interference happening here. It's just that we've got 0 plus 0. 0 plus 0 gives us 0 as a result. And also, antinodes are not positions of constructive interference, because when destructive interference happens, it occurs all the way along the wave, which includes at the positions where there are antinodes. It's just that the whole wave is 0, so it's not wrong to say that it's a position of maximum amplitude, because it is still. It's not less than the zeros anywhere else. So now we'll go on to look at standing waves in strings. When you have a string held taut with a vibration generator at one end, then you can produce standing waves, and they will occur at specific frequencies. And those frequencies will depend on the properties of the string. So length, mass, and tension of the string will change those frequencies. And those frequencies are called harmonics. They're all the frequencies at which standing waves occur, whether it's strings or pipes, they're called harmonics. Right, let's look at the experimental setup. We have a vibration generator at one end, and that will be connected to a signal generator producing a constant frequency signal to the vibration generator. That's going to move the end of the string up and down. So we'll have a wave propagate along the string towards this, a pulley. And we've got a load there, so we can adjust the tension in the string, and that the pulley enables us to transmit that tension along the string here. The wave, when it reaches the pulley, will be reflected. And what that will give us is a wave with the same amplitude and the same frequency, but that will be moving in the opposite direction to the incident wave. So then we have our two identical waves that are moving in opposite directions. And we'll start at a very low frequency with our vibration generator, and we'll increase it until we get the first standing wave occur. And the first standing wave looks like this. So at one time it's up here, we've got a peak, and then at another time it's down here, and that's a trough. So we've got a solid line and then dotted line to indicate that. Right, this standing wave is called the fundamental mode of vibration. It's the first harmonic, and that occurs at a frequency we'll call F0. And there are nodes here and here, so you always have nodes at the end. So the fundamental mode of vibration occurs when you just have two nodes at the end and then an antinode in the middle. The condition, so that's the conditions for strings. You always have nodes at either end. You can't have two nodes next to each other. There's always an antinode in between them, and you can't have two antinodes next to each other. There's always a node in between them. So we've got node, antinode, node there, evenly spread out. So the first harmonic occurs where, when that occurs, we have one antinode and two nodes. And the length of the string here, L, is equal to half of this wavelength. So this is a node to node, so there's only half of the wavelength there. I've called it lambda 1 because this is the first wavelength. Now let's increase the frequency until we get the next standing wave formed. Now we have the next standing wave formed and it follows this shape. Now we've got a peak and a trough simultaneously occurring, and at the other extreme we've got a peak and a trough there. What's changed? Okay, this is the second harmonic, which is also called the first overtone. We've doubled the frequency, so this would occur at double the frequency. And we have 2 antinodes, 3 nodes. We gained another node and another antinode. So we only had node, antinode, node. Last time we now have an antinode and node added on. And that means this length is a half plus a half. So we've got a full wavelength there. Therefore, the length is equal to, because the length is equal to the full wavelength, the wavelength is halved. We double the frequency, half the wavelength. That is consistent with what we know from V equals F lambda. So if we increase the frequency, the wavelength will proportionately decrease. And the third harmonic, I'll just be doing 3 for each of the practical situations we're looking at. We now have another antinode and node added on here. We've got 3 halves of the wavelength. So this is the third harmonic, second overtone. And it occurs at 3 times F0. So we've trebled the frequency. And we have 3 halves of the wavelength. So the wavelength is now a third of the initial wavelength. So lambda 3 indicate this is the third wavelength, because then the wavelengths are changing as we change the frequency. So the third harmonic occurs at, has 3 antinodes, third harmonic, 3 antinodes and 4 nodes. So first harmonic we had 1 antinode, second harmonic we had 2, third harmonic we had 3. And you always have 1 more node than you have antinodes. So those are our string shapes. Now let's look at pipes. Standing waves will occur at specific frequencies, which are going to depend on the type of pipe you have and the length of the pipe. So what types of pipe can you have? Then you can have open pipes. Both ends are open. And what we do to produce the standing wave in the pipe is we put a speaker on the end, which is attached to a signal generator. That will produce a sound wave which will travel through the pipe. So these standing waves in pipes, they are sound standing waves. Another misconception is that only transverse waves can form standing waves, which is not true. These are longitudinal waves and they form standing waves. So you can have longitudinal and transverse standing waves. The speaker is going to produce a sound wave which travels through the pipe here, and at the end it will refract and reflect, partially refract out and partially reflect at the end there. So the reflected wave will give us an identical wave moving in the opposite direction, which can superpose. So we've got 2 sound waves there. You can also have closed pipes. So we've closed off this end. So we've got one open end. Where the speaker is, that's considered an open end, and the other end is closed. The conditions for strings where you had nodes at either end. The conditions for closed pipes rather, you have nodes if you have a closed end. At the closed end you have a node, and if you have antinodes at the open end. Okay, so those are the conditions. We're going to start by looking at open pipes. Both ends are open, and that means you're going to get an antinode at each end. We'll go through the first 3 harmonics again. We'll look at the diagram, the frequency, the positions of the nodes and antinodes, and the wavelength. So there's my pipe cross-section. Once you've increased the frequency and formed your first standing wave, it will look like this. There's our antinode, it's a peak here, and a trough at the other end where you've got another antinode. We've got 2 antinodes, so we need a node in the middle. And then the dotted line showing the other extreme. Later on, after it's been a peak, it will then be a trough, and where it was a trough, it will be a peak. The first harmonic, which is also known as the fundamental mode of vibration again, that occurs at F0. We just said we've got an antinode node and an antinode, so that's half the wavelength. So L, the length of the pipe, is equal to the wavelength over 2. The first harmonic occurs, when it occurs, we have one node and 2 antinodes. So first harmonic, one node, and then you've got +1 antinode. Increase the frequency still, and we'll get the second harmonic, the first overtone. We now have an extra antinode and an extra node. So now, and this will occur at 2F0, the wavelength, we've got half plus a half. So we have a full wavelength in there. You can see the similarity with the strings. However, because the condition is that we have antinodes at either end, the shape is reversed. And this rule here is different. Second harmonic, we have 2 nodes instead of 2 antinodes, you see. So we've got 2 nodes and 3 antinodes. So we've got we've got second harmonic 2 nodes, and then we have +1 antinode. We've doubled the frequency, half the wavelength. λ2 is half the size of λ1. And the third harmonic, +1 antinode, +1 node. So now third harmonic, we've got 3 nodes and 4 antinodes. Tripled the frequency, and we got 3 halves. Half, half, half. So we've got 1.5 of the wavelength. So we see the same rules being followed, that if you double the frequency, half the wavelength and so on. Lastly, closed pipes. Now here we've got one end that's open, so we'll get an antinode, and we've got one end closed, so we'll get a node there. Here's my closed pipe, that's the closed end. So we get a node there, always, and an antinode there. Let's increase, so we would put the speaker on this end here. Now let's do that and increase the frequency until we get the first standing waveforms. And it looks like this. We have a node here and an antinode, which is a peak in one extreme and a trough at the other. So the fundamental mode of vibration, that occurs at F0. And there is a quarter of the wavelength there, because we haven't got 2 nodes, so we've just got one node, one antinode, so that's half of a half. At the first harmonic then we have one node, one antinode. Let's look at the second harmonic, which is the first overtone, and we get +1 node, +1 antinode, so we get this shape. So now we've got 2 nodes, 2 antinodes. This occurs at 3F0 though, and you can see that we've got 3/4 of the wavelength. So the wavelength is 3 times smaller, so the frequency that this occurs at is 3 times higher. So you can see this is different to the last 2 cases where the open pipes and the strings were following a similar pattern. The similarity in principle here is that as you go up to the next standing wave, you get +1 antinode, +1 node. So that's still happening, but because we started off with just one node, one antinode, the patterns are different. So we've got a node here going into a peak, back to a node, and then to a trough there. And then we have the third harmonic. So we add another one on of each, the antinodes and nodes. This occurs at 5F0, and the length of pipe is now equal to 5/4 of wavelength 3. So third harmonic, 3 nodes, 3 antinodes. And that's everything for standing waves, and we've now covered all of waves. I hope you found it helpful, and if you have any questions you can certainly ask those in the comments section.